Physics Final by Vedaank Tiwaarri, Jeremy Barnes, and Andre De Beer. Here's the Sun, and here is the Earth in orbit about the Sun. If we apply an impulse tangential to its orbit, we can slow down and eventually stop the Earth. Now, we are going to show you the equation for momentum of the Earth. The impulse we spoke about can be applied in one of these two ways. Either something hits us from the direction of our motion, or we shoot mass away from the Earth towards the direction of our motion. This starts out as a basic momentum equivalence, where m1v1 equals m2v2. MEVE represents the initial mass and the velocity of the Earth. The M and V without the subscript represent the mass and the velocity of whatever it is that we are shooting away from the Earth. They will be denoted as such for the remainder of the presentation. The other term is the remaining momentum of the Earth as we made it negative, just because we attempt to stop the Earth completely. Then, this term cancels to zero because the final velocity is zero. That leaves us with the mass of the Earth times velocity of the Earth equals mv. And since mv also equals f delta t, or impulse, we also get mass of the Earth times velocity of the Earth equals f delta t.
The combined mass of the Earth is 5.97 times 10 to the 24th kilograms. The linear velocity of the Earth, or our orbital speed, is 29,885.775 meters per second. Therefore, we can solve for this impulse variable right here and find that it equals 1.7842 times 10 to the 29 meters per second. So imagine our scenario where we're ejecting mass from the Earth in order to send us to our fiery death in the heart of the Sun. Let's imagine that not only do we hate ourselves enough to destroy everything anyone has ever called home, but we also really hate our oceans. So we decide to use them as the device, as our destruction with the given mass of our oceans at 1.4 times 10 to the 21 kilograms. We can find out how fast they need to be shot away, and it comes out to 127,441,483.4 meters per second, which is pretty fast, as it turns out.
If we abandon the parameter that the Earth will stop completely, we can solve our equation for the velocity at any point in time, based on any change in momentum. If we are ejecting mass in a stream at any rate, say r, in kilograms per second, then we can solve for the velocity at any given time. Then our mass term can be replaced by mass as a function of time, where m equals rt, where r is the constant rate we discussed earlier. This new equation lets us solve for any variable we want.
Here is an example of one of the applications.
Using this equation, we can take its derivative using the quotient rule to find the rate of change of the velocity of the Earth as mass hits it or leaves it. Another thing we can do with our velocity final equation is use it to solve it for the length of a given year based on our original known values of r and t, as well as the radius of the Earth's orbit. That comes out to be this. Although we aren't quite accounting for change in speed and radius resulting from our inevitable spiral of death, our model works as a reasonable approximation, and you would need this equation as a part of the more comprehensive model.
If you are interested, here's that equation's derivative, which is quite cumbersome, just to say. As a result of this catastrophe, we now turn into a world of Game of Thrones, where the seasons are longer, and remember,
winter is coming.
Okay, so our scenario is the Earth is stopped, and under most circumstances, the Earth would just fall into the sun. Now instead, let's say we want to escape our tyrant, turn the Earth into a rocket ship, and escape from the Earth's velocity. So we do escape velocity equations, gmm over r equals 1/2 mv squared, m cancels out. We end up with our velocity equation, the answer of which comes out to that. Yay.